Thank you. It's a great pleasure to be here. Especially, I thank people who have come to my seminar despite the fact I think that France is playing Denmark as I speak. And I understand perfectly if you wish to check the score as I go on. So, first of all, let me make an important distinction. I'm going to be talking about something I believe everyone in the audience has probably seen, although if you grow up going to the Mediterranean in particular does not have impressive surface gravity waves, but these are waves on the north shore of Hawaii, Sunset Beach, and I won't embarrass myself by trying to pronounce this word, which I'm told is a good French translation of swell. So swell out here, swell is the precursor or the ancestor of surf. So these are waves which were generated in the open ocean many thousands of kilometers away from Hawaii, and they've been traveling for perhaps days or weeks before they finally reach the north shore of Hawaii. And then as they propagate into shallow water, they're transformed into surf. They become bigger, very nonlinear, and they break. So I'm not talking about the spectacular surf that you're seeing here. I'm talking about swell, which is what's going on when we have mainly linear wave propagation. So the title is Long-Range Propagation of Ocean Swell. It was work that was done with Basile Gallet when he was a postdoc at Scripps Institution of Oceanography. And several people to thank for input here, primarily Walter Monk, who is a very well-known senior, he turned 100 last year, senior person in this field who did some of the initial work on this problem. And I'll talk about the history as we go along. So, as I said before, swell is deep water surface gravity waves generated by distant weather systems. And a swell is linear and looks kind of boring. So if you're thinking of a cosine model for swell, the wave slope, that is the wave number times the amplitude, is a number like 0.1, okay? So rather small angular deflections of the sea surface. And as a result, swell is perhaps best observed at sunrise and sunset when you get glancing reflections of sunlight from the ocean surface, and you can see these slight changes in angle of the sea surface. Okay? So we're talking about waves with a period between about 6 and 30 seconds. Group velocities are quite fast, which is going to be important. Group velocities 5 to 20 meters per second. Wavelengths between 50 and 1,000 kilometers. And it's important to realize that even waves which are 1,000 kilometers long are effectively deep water waves. They're waves which don't feel the bottom of the ocean, because as they propagate across the ocean, a typical depth is 4 to 5 kilometers, and the E-folding scale is the wavelength divided by 4 pi. So that length, 2 pi, the wavelength divided by 2 pi, which is still much less than the depth of the ocean, even if you have a 1,000 meter long wave, and small sea surface slopes. So the fact that the group velocity is fast is pretty important, because these are waves which are generated by extreme meteorology, large storms, cyclones and hurricanes, particularly in the Southern Ocean, which I'll talk about. And these extreme velocities allow these waves to outrun the meteorology which generates them, propagate away from the complicated meteorology which is forcing them into relatively smooth ocean waters, and propagate for long distances. Swell is essentially linear, even if on the timescales I'm talking about, and therefore it's predictable. And in fact, the proof of that is that people pay good money for forecasts, 6 or 7 day forecasts, so they can plan their surfing vacations. You can go to the web, and there's various sites like surfline.com, which will sell you a 1-week prediction of surf conditions on beaches that you might be interested in going to. And they're not bad. They're fairly reliable, okay? And that's because we're talking about a predominantly linear phenomenon here. But just because it's linear, you shouldn't think that it's weak or doesn't have much energy. So for instance, there's, let's see, there's a formula which I suppose dates from the 18th century, which is that we can calculate the energy flux in a surface gravity wave incident on a beach by multiplying the energy density of the wave times the group velocity. And when you work all that out, it's equal to the density of water, the acceleration of gravity squared, because there's one factor of g in the group velocity and another factor of g hiding in the energy density. T is the period of the wave, A is the amplitude, divided by 8 pi. And if you do all this in MKS units, that will turn out to be kilowatts per meter, okay? So you can imagine wave crests coming into a beach here, and every meter of beach is receiving this much energy in kilowatts. And if you plug the numbers with, say, a 10-second period and a 1 meter wave amplitude, which is nothing special, then the energy flux is 40 kilowatts per meter, okay? That's actually a lot of energy. And for instance, that would mean that 25 kilometers of coastline is equivalent to 1 gigawatt, which is a nuclear power station, okay? So, and in fact, this is typical of what are called high energy beaches. They're beaches like the North Shore of Hawaii, which was the picture that I showed you at the beginning, and all around Alaska and Washington and Oregon states, and I guess the shores of Portugal in the Atlantic are another example, where we typically see average energy fluxes of 40 kilowatts per meter. Now I say average because of course it's very volatile, and this number will change by a factor of 1,000 in 24 hours, okay? So huge fluctuations, but this is kind of the average power which you would look for if you were an engineer designing looking for a site where you might extract energy using some sort of device for extracting energy from the wave field. So the number is so large because all the meteorological forcing in this large area of ocean is delivered to the perimeter by the surface waves which are generated and then propagate and break on the shore, okay? So for instance, most of the sand you see on beaches is a result of grinding gravel down into sand by this energy flux. So gravity waves also have an acceleration, which is given by the following formula. So sigma is the radian frequency of the waves, and it's related to the wave number by sigma is the square root of gk. That's the dispersion relation of deep water gravity waves. Another way of writing the peak vertical acceleration is the wave slope, ak, times g. And there's only one physical constant which is going to occur in this whole seminar, and that's g. Everything can be expressed in terms of 9.8 meters per second squared. Now you can describe the acceleration with two parameters in this plane. One is the wave frequency, measured for instance in cycles per minute, say 30 cycles per minute, which would be a 2-second period, 10 cycles per minute, which would be a 6-second period, and the peak acceleration, this should be expressed in g's. There's decimal points missing in the figure. This should be 0.1, 0.2, 0.3. And the vertical axis here is quite interesting. This is what's known as the motion sickness incidence, which is the percentage from 0 to say 90% of healthy 20-year-old males who will vomit within 2 hours of exposure to acceleration under these conditions, okay? So if you're a sailor, you're interested in accelerations of about 0.1 g, so you're fortunately at this part of the motion sickness incidence diagram. And this is a paper from 1973, which is the most cited paper on the subject. Most of its conclusions aren't very surprising. For instance, the motion sickness index increases monotonically with the acceleration. However, there's one interesting remark, which is that the most pathogenic frequency is 10 cycles per minute, or a 6-second period. So that excites some sort of resonance in the ear of most people and produces the desired effect. Now, this experiment is unrealistic in at least one respect. I believe the victims were put on a vertically vibrating platform, which just went up and down like that. If you've been to sea, you know that you get rotary acceleration in gravity waves. They go round in circles, so there's both horizontal and vertical components of acceleration. And that's going to be important later in the talk. because these days accelerometers offer a cheap and very effective way of measuring the three components of acceleration in the surface gravity wave field. And from that three-dimensional measurements of acceleration, you can process the data and figure out everything about the wave spectrum, which is incident on the accelerometer. Okay? So that's how the observations are made these days with an accelerometer. So let's talk about some history. The modern history, well, of course, surface gravity waves was one of the most successful applications of fluid mechanics and mathematics in the 17th and 18th century. But I'm going to be talking mainly about what happened in the 20th century in the wave prediction problem, which really started in World War II. Okay? So in a letter from Roosevelt to Churchill in anticipation of what was called Operation Torch, which was an Anglo-American landing on the north shore of Africa, Roosevelt said to Churchill, bad surf on the Atlantic beaches is a calculated risk. So what Roosevelt meant was that the landing was going to be conducted in these vehicles which are called LCVPs. They're like amphibious landing craft, vehicle, and personnel is what the acronym stands for. And these guys tend to capsize if the wave height is more than about 5 feet. Okay, they'll just simply turn over. So indeed, during the first 2 days of Torch, about 2/3 of the LCVPs that were deployed sank when the Allies attempted to land on beaches near Casablanca. This was an unopposed landing. There was no one shooting at them, fortunately. It was just surf, which completely sank 2/3 of the fleet. Okay? So this really caught the attention of both the Americans and the British, and they both started independent wave prediction programs which were deeply classified from each other. So there was an English team and an American team who were trying to figure out how one could predict what was going to be the situation for surf on a beach, say 7 days in advance, for instance, for the landing on Normandy. When I say a team, here is the American team, Walter Monk and Harold Sverdrup. This is a photograph taken in 1940 in the Pentagon, I'm told. And the British team was Fritz Ursel and Norman Barber. Unfortunately, I wasn't able to find a picture of Norman Barber. And this quotation here is from Ursel's obituary, which was published in the Telegraph not so long ago, well, maybe 4 or 5 years ago. So these guys, with the exception of Sverdrup, who was about 40 years old, I think they were all about 20 years old. So Fritz Ursel was born in 1923 in Dusseldorf and escaped Germany and worked in Britain during the war. And as the Telegraph said in his obituary, where no ideas resulted, Ursel looked in a chapter in Lamb's Hydrodynamics and found a reference to the so-called Cauchy-Poisson problem, named after 2 19th century French scientists who had applied mathematical techniques to predict the motion of waves emanating from an instant localized disturbance, a pebble dropped in the water, for example, or indeed a distant storm. So these guys were so desperate they actually read Lamb Hydrodynamics in an attempt to make a prediction of surface gravity waves. And most of the research that was done during the war has been entirely forgotten. It was very applied and desperate. But there was one important result, which was discovered by Ursel, which was that you could really take the Cauchy-Poisson problem very seriously and apply it to the real world. So the idea is we release waves from a meteorological disturbance here, and the long waves with long frequencies travel fast, and so they will reach an observation point first. And then progressively shorter waves will arrive because they've got slower group velocities. And so if you make measurements at a fixed location, which is distant from the source of the waves, then you will see a well-defined signal in which the long frequencies arrive first, the long period waves arrive first, and in fact, the frequency observed as a function of time is given by this formula. it's g over 4 pi r, where r is the range, the distance between the observatory and the storm, multiplied by t. So if you're teaching a class on linear wave propagation, this is a great homework assignment or an exam question to set for students to show that as a result of the linear dispersion relation, the frequency changes with time in just this way at an observatory, okay? So in other words, if you're a linear wave theorist sitting at the observatory, you can infer the range by measuring the frequency as a function of time, and you can check that your theory is working by verifying that the frequency is changing linearly with time. The fact that the frequency changes linearly with time is a special property of this dispersion relation, and it's not the case if I had some other power of k in the formula, okay? So here is an example of the application of the formula. This is a meteorological chart from March 1945. The British had a wave observatory here in Cornwall at the tip of Britain. And as Ursel and Barber said, the linear theory is reasonably accurate. That is, they did in fact see a linear change in frequency with time. But the area of the storm is too great. So here's the storm on this weather map. The area of the storm is too great, and it's too close to the observer to treat this as a point source, obviously, okay? I'll show you some real data later. This is the schematic. So, but the wave propagation diagram is a plot of the observed wave frequency as a function of time. You measure the slope. If the frequency is in hertz and the time is in seconds, this is the formula which gives you the range. So after the war, Munk initiated a program looking at long global scale wave propagation, which was run from Scripps Institution of Oceanography. So this is the first of many figures which I'm going to show you, which use a very strange projection. It's not a Mercator projection. The observations are made in an island called Guadalupe Island, which is offshore of Mexico. And this is a projection which is centered on Guadalupe, and great circles which pass through Guadalupe Island are straight lines in this map projection. It's called an azimuthal projection. So with the formula for the range, Munk and Snodgrass in 1957 inferred they were seeing waves on the beaches of Guadalupe Island from 14,800 kilometers away. Now, the trouble with that number is that it's too big for the Pacific Ocean. That is, if you actually draw a great circle at a range of 14,800 kilometers, there's only a very narrow set of places which remain in the ocean where those waves could have come from at that range, and that's actually south of Australia in the Indian Ocean, okay? It's not clear from this projection, but these points here actually correspond to points which are south of Western Australia. So according to Munk and Snodgrass, the observed frequency shift is consistent only with very distant areas of generation in the Indian Ocean south of Western Australia. So this was the first indication that waves which were generated in the southern hemisphere could propagate, say, 1/3 of the circumference of the Earth and break on beaches in California. So the trouble with the range propagation diagram is that it gives you only the range. You have no directional measurement. So that was the problem with this inference here. You had no idea where the waves were actually coming from. All you were doing was measuring the frequency at the observatory. So in an attempt to improve on this, in 1963, the same group of characters from Scripps Institution of Oceanography developed, well, the idea here is it's very similar to astronomical interferometry. You put 3 pressure gauges on the bottom of the ocean, and they form a triangle. I realize you can't read the numbers here. So the side of the triangle, it's 900 feet, so it's, say, 300 meters or so is the side of the triangle. And then as a group of waves impinge on the triangle, the signal will be, there'll be a phase lag as the waves pass the 3 different points on the triangle. And from the phase lag, you can infer the direction. Okay, so it's exactly the same technique, I think, that astronomers use to work out the direction of radiometric measurements on the Earth. So you have three different detectors. and you look for the phase lag between the different detectors. 3 is the smallest number you can use because, of course, if you've got a wave crest which comes from this direction, it will hit those 2 points of the triangle simultaneously. And if you only had 2 measurements, you wouldn't see a phase lag. So this was the attempt to actually add direction to the measurement. And, well, it didn't work very well at all, which is the subject of the rest of the talk. So the problem with direction. Some of the inferred sources were at least 10 degrees away from where storms were actually located on weather maps. So the solid points here are where the meteorologists told us there were storms in the storms around Antarctica. So here's Australia, Antarctica. I think the ice edge is probably shown on this map somewhere. The ice edge in October, for instance. Some of the storms had to be displaced quite a distance from places where there were actually, some of the inferred locations had to be displaced quite a distance from where there were actually storms on the weather map. Some of the inferred sources were on Antarctica, which is crazy. It's impossible. If you have a storm on Antarctica, it's not going to generate waves. Some of the storms were on the ice, and on the sea ice, which is a very effective absorber of waves, and so you wouldn't expect a signal either. So the mystery was that the swell did not seem to follow great circles. In other words, if you measured the direction of the incident swell at Guadalupe Island and then backtracked along a great circle, you ended up saying that the storm was here, whereas in fact it was over there. Okay? So that was the situation. When Basile came to Scripps as a postdoc, I think Walter Munk had been brooding on this, well, since 1957. So that was 60 years of agonizing about this problem. And he suggested that we should really look at modern data and try to redo this. So that's what this is about. It's much easier now because, as you'll see, there's a free source of data. And we're going to look at modern data and ask, are there really directional errors associated with great circle backtracking of storms? Okay? Great circle backtracking of wave observations. So there is now a whole network of accelerometer buoys deployed off the coast of the United States and off many other countries. I don't know about the situation in Europe. These are buoys which, first of all, are in deep water, and this example is our favorite buoy, which is located here. This is the site of the historic measurements. This is one of the islands where Munk and Co. had a wave observatory back in 1963. So we're quite close to this island, which is, I think, Catalina Island. Here's San Diego, which is where I'm from. And this buoy has a 3-dimensional accelerometer. It's been making directional recordings of swell and measuring the height spectrum every 20 minutes since 2004. And the data is then telimited to shore where we can get it. And there's a directional spectrum, which means there's frequency bends, and we can get a mean direction of incident waves on this buoy for each frequency bend in the data. I'm sorry, and the island is actually San Clemente. Is that what I said? I think I might have said Catalina. This is San Clemente Island. So we're going back to the 1950s and 60s, and we're plotting the wave propagation diagram. We have time in days. These are year days, day 262 in the year. I forget which year this was from. So what Basile did, he went through the data and he looked for examples of very clean storms, examples where we could see a very distinct signal. He threw most of the data out. He was looking for spectacularly clean examples, rather like this one, where we see a nice linear slope on the wave propagation diagram. We used the formula which was derived by Ursel based on the Cauchy-Poisson solution, and we can work out the range. Now, we also get a measure of the direction. So this is the direction of the waves which are incident on the buoy. So we don't have to use this cumbersome triangle with pressure sensors on the bottom. We're inferring this from doing signal analysis of the accelerometer. And what we see is when we have a nice clean slope on the wave propagation diagram up here, we see fairly substantial plus or minus 10-degree fluctuations in direction incident on the accelerometer. So we believe there's physical information in the fluctuations in direction, which I'll come back to later. But what we're simply going to do now is take the average direction. Okay? So now we know the range and we've got the direction. We can backtrack along great circles, and we've got much better meteorology now than they had in the 60s. So the European Centre for Medium Range Weather Forecasting, as part of their weather forecast, they forecast what's called significant wave height. So this is the surface wave height in the ocean around Antarctica. Here's Antarctica. Here's the ice edge, again from the ECMWF map. And notice the wave height is 10 meters. These are big waves generated by a huge storm south of Antarctica. And most of the examples that Bazile looked at were exactly like this. The inferred source we got from making measurements off the coast of California was here at the red dot, and it was generally right in the middle of the ECMWF forecast. An amazing agreement, in my opinion, because there's no way that the buoy, there's no way that this particular buoy knows anything about the ECMWF forecast and vice versa. These are two independent measurements of the same thing. So excellent agreement on the whole. But there are a few much better agreement than Monk and co. found 40 years before. But there are a few anomalies. So here's one. Here is one where the storm apparently was on New Zealand, which New Zealand is always a problem, actually, especially if you're an Australian. And the storm was over here, okay? So this is the sort of problem that Monk and co. had seen 60 years earlier, where there was a fairly substantial distance between the inferred source and where the source actually is on the weather map, okay? And of course, if the storm really was centered over New Zealand, there wouldn't have been a signal generated at all anyway. And it's worse than that, because if you take this storm and follow the Great Circle, that's this path here, 210 degrees. This is 210 degrees measured from the north to the buoy off the coast of California, and you follow that Great Circle from this storm, in the way you'll pass right through a very dense island group called the Tuamotu Islands, which is part of French Polynesia. So in other words, the Great Circle path from this storm to the observatory is in principle blocked by this island group, so there should be no signal at all. I'll show you a picture of Tuamotu later. And so this is a problem. Okay? Why are we seeing anything at all, let alone why the source is on New Zealand? So to summarize there, the modern buoy results are actually much better than the bottom pressure measurements of Monk and Snodgrass, but there are still some issues. So then why don't waves follow great circles? Well, why do some waves not follow great circles is the question. So here are some of the suggestions. The rotation of the Earth means that the dispersion relation I'm using, root GK, is only an approximation, but it's a very good approximation. And if you carefully calculate this effect, which was done by Backus back in 1962, it's far, far too small by factors of 10 to the 6 to explain any sort of anomaly. The Earth isn't a perfect sphere, but that's even less important than rotation, as it turns out. Here's one which is crazy, but it's awfully difficult to explain why it's crazy, because it sounds plausible when you first hear it, which is that surface waves, as they propagate, can carry mass with them. There's a phenomenon called Stokes drift, where a surface wave will actually transport mass. And so if it's transporting mass, there should be a Coriolis force acting on that mass transport, which will send the packets round in circles, and they shouldn't actually get anywhere. This effect is wrong. The argument I've given here is wrong, but it's awfully difficult to locate the mistake in this argument. So it's a question of wave interaction with currents generated by the waves themselves. Refraction by bottom topography, this is almost certainly important. So back in the historic measurements, this was definitely important. And Walter, I think, when he was 98, finally got around to correcting his mistake and published a corrigendum. He was the only survivor of the 5 original authors. So Monk 2013 is a discussion of the effect of bottom topography on those measurements, which were made in 1963. However, that can't explain the issue that we're seeing because the measurements we're using are in 2,000 meters of water. So our hypothesis, which I'll talk about for the rest of the talk, and how's my time going? How is my time going? What? Sorry? Okay. Is that refraction by the surface currents between the source and the receiver is the main issue, okay? So this is a good place to ask questions because I'm going to start talking about some more theoretical things at this point. So if there are some questions for clarification, this would be good. No? All right. Yes?
What about interaction with the wind
Yeah.
as the waves propagate?
Yes.
Is that important?
We believe not. You can, of course. Yeah. So the question was, what about the interaction of the wind, interaction with the wind as the waves propagate? So there are two possibilities. The one which was discussed at length by Monk and Co. was to treat that as dissipation. Apparently that doesn't happen very effectively because otherwise we wouldn't see a signal. So you might think there's friction with the wind which would dissipate the waves. Now, I'm going to be talking about refraction of surface currents by ocean currents. So the U here is the velocity of the water. Now, of course, as a wave propagates on the interface between air and water, there's an expression of the wave in both the air and the water. And so really, the wave will be affected by wind as well as by ocean currents. Now, you can work out the effect of that, and what the velocity, which is really important and which really affects the propagation of the waves, is a density-weighted mean of the velocity in the air, which is weighted by the density of air, which is 1 kilogram per cubic meter, and the density of water, which is 1,000 times larger. So because of that effect, it's true that the wind is faster than ocean currents, but it's not 1,000 times faster, okay? So most of the effect, we believe, is due to refraction by the currents in the water, okay? Notice that this is a small parameter, so typical ocean current speeds are maybe 10 centimeters a second, whereas the group velocities are much faster, 10 meters a second. So there's a small parameter here. So this is a question of how can this relatively small parameter produce the observed deflections? It could be that the wind is a contributor to this, but we believe it's a secondary effect. Other questions? No? Okay. Yeah.
Why the source should be that localized?
Yeah, well, actually, if you look at the...
Saying that storm is a huge thing and the signal could be complicated.
Yeah, so that's true. This is an extensive storm, but it's quite a long way away from the source, so we are treating it as a point source effectively. And I'll talk a little bit about the extent of the source later. That is an important thing. So you could think that some waves from this side of the storm are perhaps avoiding Tuamoto, the Tuamoto group, and you're actually getting ahead of my explanation. I'm not going to treat it purely as a point source. But on the other hand, when we do this with 18 clean signals and we see 14 of the 18 look like this, it's awfully tempting to treat it as a point source with some sort of center, which is effectively what we're seeing. So what we're going to do, we just want to get some idea of the order of magnitude of things and whether it's really possible that waves where this parameter is maybe 1 on 1,000, surface currents for which this parameter is maybe 1 on 1,000, can produce the observed deflections. We're going to use ray tracing. We're going to use WKB if you like. So this would be the displacement of the surface of the ocean. There's an iconal function or a phase function, and we have the ray tracing equations. Here's the Doppler shifting term in the dispersion relation. Here's root GK. K is the total wave number, so it's the square root of p squared plus q squared, the x and y wave numbers. We're going to treat u and v as independent of z, which is also an approximation because, of course, surface currents in the ocean do depend on z. And this then gives us the the ray tracing equations, which we're going to solve, this coupled system of ordinary differential equations to trace rays. And to do this, of course, we actually need surface ocean currents. We need U and V, which are functions of x, y, and t. Okay? So we're going to use a product that is something which is worked out by combining data from satellites and from surface drifters. It's called OSCA, Ocean Surface Current Analysis in Real Time. And it provides you with an estimate of surface currents in the ocean at either high resolution, which is 1/3 of a degree, in other words, a little arrow, a little vector, which is the surface current in a domain which is 1/3 of a degree on a side. I think you get a product like that once every 5 days. And there's also a low resolution version. Naturally, we use the high resolution version. The answers are quite different. And as I said, the high resolution is not all that high. So probably what we're doing is not very accurate. I would say that it's really just a way of getting an order of magnitude effect of the deflection produced by these sort of currents as waves propagate through the surface currents in the ocean. So for example, here is one of the, oh, and by the way, the color in these maps, it's very fortunate. The color in these maps, which is something which is also routinely estimated by the satellites. It's the vorticity, the vertical component of vorticity of the currents in units of seconds to the -1. And as we'll see later, the vorticity is one of the prime variables which is responsible for distorting the ray paths. So here's a source, which is a point source at the moment. Here is the observatory, which is the buoy 46086. And this is one of these azimuthal projections where a great circle, which is passing through the observatory, would be a straight line. So in this map, we have shot six rays from the source. One of them has gone through the observatory. Okay? So you can see it's taken a path which is very far from a great circle. It comes into the observatory, and then if you're following, if you great circle backtracking, you draw the tangent to that path, and you go on a great circle, and you end up on the ice. Okay? So in this example, this is a clear case, well, this is an illustration, I guess, where the deflections produced by the surface currents produce a source which you would put on Antarctica, according to this figure. Okay? And these are 6 other paths taken by rays leaving the source. None of them follow great circles. In fact, if you look at the paths, I think you can see, for instance, in this path here, there are some scattering events. There are a small number of events. Here's the first one where the ray changes direction. And here's the second one, maybe 2 scattering events, which bend this ray so that it follows a non-great circle path and ends up at the observatory. So this is an animation of 20 years of OSCA data. You get an estimate of the sea surface currents every 5 days. This is a point source. I'll talk about extended sources later. And what you would see at the observatory is rays coming from a lot of different directions bombarding you. And if you took the mean of those directions, that would give you a source which is moving around like this. So the basic idea, and of course this is a point source, which is exaggerating the problem, but the point is even with a point source, if you take the mean of the directions, it's an unbiased estimate of the location of the source. So in other words, there's no systematic error here. If you do enough averaging, you will, in fact, get the right location for the source. Okay? Yeah?
It should depend a little bit on the current, no?
Well, it depends a lot on the currents if we play this again, right? There's a different realization of the currents every 5 days.
But in general, there should be a bias estimate.
We need a microphone.
Oh, okay. Can I repeat the question? Yeah, so the question is, why isn't this, the estimate here should be a biased estimate of the location of the source. So what I'm saying is, if I stop this now, I don't know if I can stop it. No, I can't. in general, it's not biased. You see, if I'm making measurements here, I'm going to see, say, plus or minus 10-degree fluctuations of stuff coming into the observatory, which is actually what we see in the directional spectrum from the receiver, okay? So because I've got equal numbers of ray paths coming from one direction versus the other, I would say it's an unbiased estimate of the mean. Now, it's going to be in a single realization like the one that concludes this movie, you're going to see that it is biased, so it's not a good example of what I'm saying. But in general, with enough averaging, there is no bias in the estimate, okay? Yeah?
Why are there several lines? I would get that you would have only one direction at a time. Is there a focusing effect here? Or is
this is well known in acoustics. This is what's called a multipath, okay, which I think is something, this is part of our hypothesis here, is that there's a multipath that is several, or in this case, quite a few, I can't really count them, but order of magnitude, we've found 10 different paths, 10 different non-great circle paths, which connect the source to the receiver. And it's simply that the rays are propagating through a very complicated environment, and there's multiple connections between the source and the receiver. So that's the point here. The source and the receiver are connected by a multipath. So what I'm saying here is if there's 10 rays, it's true that some of them have taken this very misleading route and ended up at the receiver, but many more in this particular realization have gone on a fairly straight route, and with enough averaging, you will get a good estimate of the source. And in fact, if we have an extended source rather than a point source, the effect is even better. There's much more averaging in an extended source, okay? So the idea here is individual rays do not closely follow great circles, but the collection of rays emitted by an extended source does provide a good, unbiased estimate of the source location. And that's kind of what we see in the data, because we do see plus or minus 10-degree fluctuations changing on a time scale of minutes arriving at the receiver. And our inference of the source is always obtained by averaging over those arrivals. So the idea is that incoherently emitted wave packets travel along different rays and they bombard the receiver. The angular width of the multipath, that is the width of the rays which are coming into the receiver, is actually much larger than the width of the storm. So if you followed back the angular width here, you'd get a huge area here, which the storm would be at the center of it, and hence the observed fluctuations in direction seen at the receiver, okay? So here's what the densest part of the Tuamotu island group looks like. This is a rather fanciful figure from the paper by Snodgrass and co. I think this is the wave shadow cast by Tuamotu. So the idea is refraction by the surface currents produces the multipath, and the direction of the incoming swell at the receiver fluctuates. The mean direction is reliable, except if the multipath is partially blocked by, say, an obstacle like the Tuamotu group, okay? So then partial obstruction of the group, partial obstruction of the multipath would explain why, first of all, you even see a signal at all at the receiver when Tuamotu is in the way. Because the multipath is so wide, the island group can obstruct, say, half of the multipath, but you still get the arrival from the other half of the path. So that produces a bias at the receiver and essentially a mirage. Okay? So this is a typical obstacle, which is the Tuamotu group at the direction of 216 degrees. By the way, you can see that this paper was written in a completely different scientific environment than the one we now live in. This is figure 50 from the paper, and it's not even half finished. So let's talk a little bit about theory. How can weak currents have such a strong effect? And even if you don't care very much about surface gravity waves, perhaps you're interested in isotropic wave propagation through a moving medium, like acoustics, for instance, I don't know. There is a result which applies in the weak current limit. This is the weak current limit, where the speed of the velocity of the fluid is much less than the group velocity. And it's an important general result. it's in Landau and Lifshitz Fluid Mechanics in the chapter on acoustics, and it's been independently discovered and published by several people, so it's in JFM. And before explaining the result, I'll first of all show you a simple exact solution of the ray tracing equations, which shows that the current speed is irrelevant for bending waves, okay? And this is perhaps interesting historically because it's wrong in the theory of sound. It's one of the two big mistakes in the theory of sound. The result is very simple. It's kind of trivial, really. If I have a uniform current, a uniform flow, and here I'm doing things in a Cartesian geometry with a source and a receiver, and simply a uniform flow sweeping past the source and the receiver, then the ray which goes from the source to the receiver is a straight line no matter what the speed of the current is. Okay? So that's a trivial solution, I would say, of the ray tracing equations where the wave numbers don't change with time because changes in the wave number rely on gradients of the velocity, and there are none. So P and Q are constant, and therefore dx dt and dy dt are also constant. You can eliminate time, that gives you the ray path. It has to be a straight line, and it is. Okay? So from a purely logical point of view, the speed of currents is completely irrelevant to ray bending because no matter what the speed is, the rays are straight. Okay? So what properties of the current are responsible for bending rays? It turns out, this is the result from Landau and Lifshitz, that in the weak current limit, and provided that we have waves with an isotropic with an isotropic dispersion relation, that means that omega depends only on the magnitude of the wave number, the square root of p squared plus q squared. The radius of curvature of the ray is equal to the group velocity, d omega dk, or the magnitude of the group velocity, d omega dk, divided by the vorticity. It's easy to remember because of the dimensions. This is the radius of curvature, so it has dimensions length. So in other words, if I have a vortex, which here is the concentrated vorticity of a vortex, there's going to be a 1 over r irrotational current surrounding the vortex. You shoot in a ray, and it travels on a dead straight line, ignoring the 1 over r azimuthal current which surrounds the vortex. So there's certainly velocity out here. It hits the center of the vortex where all the vorticity is concentrated, and that's where it bends according to this formula from Landau and Lifshitz. Okay? So ray curvature is independent of ray direction and of current direction. In other words, there's no anisotropy despite the direction of the velocity. So this is the closest thing we have to something like Snell's law, which you can use to build some sort of intuitive picture of wave propagation in a moving medium. And it works spectacularly well. So in this picture here, we're comparing an exact solution for wave ray propagation through complicated surface currents. I think that's the blue curve shows the curvature, 1 on the radius of curvature. The blue curve is the curvature from an exact solution, or sorry, a numerical solution of the full ray propagation equations, and the dashed curve is the formula from Landau and Lifshitz, and they're right on top of each other to within the line width of the integration. So, and this, I think this diagram also shows you that refraction, that is bending of the rays, is really due to really 3 current systems located between a typical source in the Southern Ocean and the receiver off California. There's lots of vorticity in what's called the circumpolar current. So we see lots of ray curvature down here in the Southern Ocean as waves propagate through these very strong currents which surround Antarctica. Then there's a frontal zone in the South Pacific, which is responsible for some secondary maxima here. And finally, right on the equator, there's lots of vorticity, which produces additional curvature of the rays, okay? So it's incorrect to think of this as a random walk where there's a lot of small deflections. What's happening is there's 2 or 3 big deflections which produce the errors at the receiver. It's not the accumulation of one or of many small errors. It's a very small number of large errors, large deflections, which are making this happen. And in fact, most of the final errors, most of the final deflections are due to what happens after the rays cross the equatorial current system. After crossing the equatorial current system, the rays which arrive at the receiver travel more or less on great circles. Okay? So thinking of that, here's what we think was happening back in 1963. First of all, the observatory here is located in rather shallow water, okay? And there's some offshore obstruction, which this is the submarine topography. And so if I'm launching 3 different rays from a source down here, in principle, all 3 of them would follow this simple multipath and arrive at the receiver, rays A, B, and C, A, B, and C. But rays coming from the direction of A, and I've shown deflections occurring only at the equator in this simple example, rays coming from direction A will be systematically blocked by the shallow offshore topography from the receiver. So in other words, the rays which actually show up in the historic measurements are rays like B and C, which are systematically biased. And in fact, there was a systematic bias in the inferences, which explains what's happening at this point. So that's, I think, we believe that's probably what was explaining the problems we saw back in the 60s. And that's the end of the talk. Thank you.
Yes. So from what you're saying, there's never any reflection on the coast. Every wave which arrive on the coast is destroyed.
We know there are some reflections because I don't know. We see what are known as microseisms off the coast of California, which mean it would take a little while to explain what a microseism is, but it's a clear signal of some reflected waves coming back from the coast. So what we're saying is most of the waves are not reflected.
Okay. And when a wave breaks on the coast, do we know where the energy goes?
Where the energy goes to making sand from gravel, grinding down
most
rocks.
of the energy is doing that.
Yeah.
There's no heat, no other things.
Heat, yes. Actually, you know, the numbers are so extreme, right? So the number that I estimated back here, I'm glad you mentioned that, actually. It is kind of interesting. Got to go right back to the beginning, to my 40 kilowatts per meter and 1 nuclear power station every 25 kilometers of coastline. This is with the 1 meter waves, but they could easily be bigger by a factor of 3 or 5. So you should be dividing 25 kilometers by 10 or 25. So imagine there's a nuclear power station every 5 kilometers heating up the water when they break. Yes, people claim they can actually see joule heating of the ocean water due to the dissipation of this energy as the wave breaks. There's possibly a very small temperature. See, it's one of the few examples in geophysics where you might actually be able to see joule. You know what I mean by joule heating, just breaking the waves, heating up the water, because this is such extreme numbers.
And I have a last question, which is why is there a band of vorticity at the equator? Is it known?
Yes, because there are very strong equatorial currents, strong shallow equatorial currents. Yeah.
Isn't there any effect of like the scattering of the waves associated with when it encounters, say, packets of vorticity?
No, that effect is probably very, very weak. You might wonder about, I think you would wonder about this rather fanciful figure from Monk & Co., which doesn't show any diffraction as the waves travel around the Tuamotu group and doesn't show any reflection. First of all, many of these islands have, well, first of all, can we work out the scale? The typical scale of an island here is maybe about 40 kilometers, so they're substantially larger than most of the waves. So which is why they're ignoring diffractive effects as the waves propagate around them. I think probably as a zero-order description, that's correct. And we don't see, There probably is some reflection as well of the waves as they encounter these islands. To the extent that some of these have very shallow coral lagoons around them, though, so they're islands which are surrounded by coral reefs, they're very good absorbers because the waves go over the coral reefs and break in the lagoons around the islands.
So I have 2 questions. So do you know how intense should be maybe the shear or the change in velocity or the intensity of the velocity in the currents, or how large they need to be? And the second question, in this equatorial countercurrent as well as in the ACC, so in the Antarctic circumpolar current, there are a lot of eddies.
Yeah.
Do they have an influence or not?
Sure. Well, that's the beautiful thing about the Landau and Lifshitz formula, right? You've immediately got an easy prediction of the wave path, sorry, of the curvature of the ray. Now, it does rely on WKB. So if you have really small-scale vortical features, eddies whose size is comparable to the wavelength of the waves, say 1 kilometre for a really long wave, then you probably can't use the formula with a clear conscience. But you know, to get a 10-degree, to get a 1 or 2 degree deflection over several thousand kilometres builds up to a very substantial error in the direction. And I think that's what we're seeing in diagrams like this. I think the Oscar data is not very good. It's only got a 1/3 of a degree resolution, so it doesn't resolve many of the vorticity carrying features in the ocean. But even that under-resolved measurement of the vorticity shows substantial curvature of the rays.
And I have another question. So about continental slopes, I think that you have ridges between these Southern Ocean points and your observer point.
Yeah.
There is no influence at all on the topography.
You mean as they go over the East Pacific rise?
Right.
Yeah. Well, I'm actually embarrassed that I don't know if the Tuamotu group is a surface expression of the East Pacific rise or not. I think some of the islands probably are, but the trapping is exponential, and so
it's they need to be very close to the surface.
They need to be very close to the surface to affect the waves. So I think maybe you can tell me what the mean depth of the mid-Pacific
I think they are
is.
Deeper than 1,000 meters from
so
the surface.
It's probably a negligible effect.
I just had a comment. I used to live in Hawaii, on Oahu, and I'd often look down at things like that first slide of yours. And the thing that came to my mind is the analogy with intensity interferometry, which was Hambry, Brown, and Twist used radio telescopes to determine the size of stars without doing phase interferometry. Oh. And it's the equivalent that what you see is these beautiful organized sets, but they have a certain time scale. You know, the sets don't last forever. And there's a correlation in the power as you look along the coast. So it seemed to me a beautiful illustration of something that our students often find very difficult to understand, this intensity interferometry.
I'm not sure I understand it very well myself.
Coming back to the wind, though, if I may.
Yeah.
I mean, it seems to me you could have situations where there's a following wind with a speed which is similar to the phase velocity. Isn't there then going to be some kind of resonant coupling, if you like, when there's a matching of those speeds? It's just a sort of gut feeling, but...
Yeah, so that of course is what actually happens when they're generated by meteorology. So when I say the atmosphere doesn't have any effect, of course that's obviously not true because we wouldn't have waves like this without the atmosphere to generate them in the first place. But I think you've got some sort of a storm which has finite extent and which to a large extent can be thought of as a big eddy. And the waves, once they're generated, the wind doesn't follow them. They head off on ray paths in various directions. And also, this is an extraordinarily clean example. Most of the time we don't see things like this, of course. We see, as you said, sets of maybe, I don't know, 2, 3, 4, 5 waves coming in, and then that'll stop and they'll come in from a slightly different direction, and they won't be as beautifully long-crested as this example.
The last question is about imagery, SAR, imaginary. If you I know that people in Ifremer are working on the sunlight reflections to see really discontinuities in the ocean. So maybe from these images you can have pictures along the track of this wave packet.
Absolutely, which is yet another paper by Monk, who was the first person to realize that you could, by looking at the statistics of twinkles on the sea surface, you could work out the slope, the mean square slope of the sea surface. And more than just the slope, the statistics like the kurtosis and the skewness of the sea surface.
Maybe you can follow them really from one point source to your, with
I see.
many
You can actually
images,
follow
right.
an individual wave packet. Yeah, I don't know about that.
I don't know the frequency of the images, but...
Yeah. Maybe, I think we probably don't have satellite data that's good enough to do that. Yeah.
Thank you very much again, Professor
Thank
Jung. So this is the last colloquium of the year, and next year we will have new organizers with a new season. Thank you again for those 2 years.
Thank you to you.